So what will homework look like, you might ask? Okay, let's get to it. So here was the logistic growth model, our differential equation, the solution, the how we calculate C, right? It's all there. Lots of different angles that questions can take. So let's start off with something fairly straightforward. It says a fish population has a carrying capacity of 6,000 with K equals 0.0015. So they would have found that K just from maybe collecting data. And they tell us that time is in years. And so the first thing they asked us to do is write the logistic differential equation. Well, okay, all right. All you want me to do is write the differential equation for this one. Yep, just write it. Just fill in all the different pieces. And we're just kind of letting this idea gel. How do all these parts here that we just learned, how do they fit together? Well, nothing too crazy here. dp over dt equals our k value times p times the quantity 1 minus p over, and our carrying capacity is 6,000. So there's our differential equation. Part B, if the initial population P naught equals 1,000, find the population size in 50 years. Okay, well, to find the population size, then what we need is the solution. And for the solution, okay, we know K, we know M, we'll need to know the C as well to plug in, and then we can plug in 50 years and we will have it. So I'm just gonna state what we know so far. The solution P equals, in our carrying capacity, 6,000 over 1 plus C e to the negative K 0.0015 T. Okay. We need to know that C to plug in, right? So we know C equals the carrying capacity divided by the initial population. So 6,000 over 1,000 minus 1. And that works out very nicely as C equals 5. So we can put 5 in. And finally, now to answer the question, what's the population after 50 years? We can plug 50 in for T, and I just went ahead and knocked that out. When I plugged in 50, I got 1064.07. It makes sense for these questions. You're talking about population, just to round it to the nearest whole number. So in this case, I think we can say there'll be 1064 fish at that time, which is not very many, right? I mean, they started at 1,000. 50 years later, there's 1064. Maybe it's that value of K. Maybe that's just a very small K. And so they're barely growing here at the beginning. I think they're getting faster and faster as time goes on, but just barely creeping at the start. Okay. So there's one example. What else might you see? Let's take a look here. Suppose a population is modeled by, and they give us the differential equation, dp over dt equals 0.4p times the quantity 1 minus 0.0025p with initial population p naught equal to 50. Okay. Well, what are they going to ask? Part A, what is the carrying capacity? What is the carrying capacity? Well, you notice that it's not immediately available for us. We're going to have to go figure that out on our own. How are we going to do that? Well, if they gave us the differential equation, right, we can look back here. Carrying capacity is M, so we need to look at that second term. But you notice they didn't give it to us in the traditional style. They gave us 0.0025p, so could we adjust that to figure out the carrying capacity? And well, sure, yeah. 0.0025p is the same as p over 400. You could take 1 over 0.0025 to figure that out. So there's our carrying capacity right there, 400. All right. Part B. Ooh, this is interesting. When will the population reach 50% of the carrying capacity that we just found? When will the population reach 50% of the carrying capacity? So we just found the carrying capacity is 400. So, of course, we're looking for when will the population reach 200. But there's a little bit more going on than that. So we look to our solution to the differential equation that describes the population size, right? P equals m over 1 plus c e to the negative kt. And we notice there are several things we need to fill in. The m we just found. The k, we got to figure out what k equals. And finally, c, we got to plug numbers into all these. And well, we kind of talked about what p is. It's just going to be half of m. So we just found that m is 400, which means p is 200, of course. We can quickly get c. C, if you'll recall, is the carrying capacity divided by the initial population minus 1. And so they told us that initial population back here was 50. So that comes into play at this point. Turns out that's 8 minus 1, which is 7. And finally, k. Well, they don't tell us k. They do and they don't, right? So we got to look back to the differential equation. Turns out this number here is the k. If you compare that with the differential equation general form, that number in front of that p there is the k. So we know that k is 0.4. And all right, I think we can go for it at this point. We can plug all those numbers in. 200 equals 400 over 1 plus 7 e to the negative 0.4 t. And of course, our job is now to solve for t. When will this population reach 200? So, all right, not too bad. We can multiply this whole thing over there. We can divide by the 200 and get 2. We can subtract 1, divide by 7. All right. And I'll go through this pretty fast, right? Natural log. And finally, divide by negative 0.4. And I just went ahead and crunched that and got 4.86 years. So this population, we're not told what it is exactly, but initial population 50, and only less than 5 years later, it's up to 200. So that's doing pretty good. It had a higher value of k, right? Not that much higher, though. Okay, so it turns out I've got one more question for us. This is an interesting one. What is the rate of change of the population at t equals 0? Exactly how fast is the population size increasing at time 0? How are we going to figure this out? Okay, so what we'll have to do is go back to the differential equation. Why is the differential equation needed here? Because we're not talking about the size of the population. We're talking about the rate of change of the population, and that is described by dp over dt. What is the value of dp over dt when time equals 0? And you're like, okay, well, that doesn't sound too bad. But you look for a second. Wait a second. dp over dt, there's no time here. There's no t. It's just p's. What do we do? I can't plug in 0 anywhere. Well, that's true, but do we know the population size at time 0? And of course, plug in the initial population for p, because that would represent the population at time 0. And we know that to be 50, so we can plug in 50 for the p's. dp over dt equals 0.4 times 50 times the quantity 1 minus 0.0025 times 50. And we can get an answer right there. I got 17.5. dp over dt equals 17.5. And if you're wondering what that represents, not too hard to see, right? We can go back to the way the derivative is set up. So it's the population. They don't tell us what this is a population of. A lot of times they use fish, but it could be who knows what. So I decided to put units, right? Whatever these things are. I didn't know what word to use there. Individuals did not seem to make sense because that's really people. Like subjects, I don't know. And time is in years. So units per year, 17.5 units per year is how fast the population is increasing at time zero. That said, it does get faster in those first few years, and then it starts to dip back the other way and slow down as you get closer to, in this case, 400. Okay, that's it for 9.4. Check out the homework.